Hello everyone. In this video we will be discussing vectors, particularly from a context of physical quantities, which we'll often be seeing in Physics 151. Vectors are quantities that have both a magnitude and direction. This magnitude is often the numerical value associated with the vector, or visually speaking, the length of the vector arrow. Quantities that we are familiar with at this point, like displacement, velocity, and acceleration, are all examples of vectors. To get us started, consider a biker who is moving at 5 meters per second in a direction 60 degrees north of east. Let's let this dot represent our biker. From here, we can draw an arrow representing the velocity of this biker. The arrow should be pointed in the direction of motion, which according to this example is 60 degrees north of east. And how long I've drawn my arrow represents the magnitude of their velocity, which is the 5 meters per second. This question is interested in how quickly the biker is moving eastwards, or to the right in this case, as well as how quickly they are moving northwards, or in the upwards direction. So in other words, how much of this 5 meter per second arrow is in both of those directions. Whenever we are trying to think about how much of a vector is in certain directions, we break it up into a right triangle, which has some horizontal and some vertical parts to it, which we call components. The original vector is always the hypotenuse of the right triangle you draw using these components. Since we know the hypotenuse of this triangle as well as an angle inside of it, we can use trigonometry to find these components. The horizontal, or x component, I'll call it, will be the adjacent side to the 60 degrees. So using SOHCAHTOA to relate the adjacent side to the hypotenuse, I would use cosine of 60 degrees is equal to that horizontal x component of the velocity divided by the hypotenuse, which is 5. Moving things around, I can solve for the horizontal x component, which will give me 5 times cosine of 60 degrees. Plugging this into a calculator, we will find that the eastward, or x component, of this velocity is exactly 2.5 meters per second. Meanwhile, the vertical component, which is the northward part of our velocity, which I'll call Vy for the y component, is the opposite side of that 60 degree angle. So using SOHCAHTOA to relate the opposite side and hypotenuse, I should use sine of that 60 degrees equals the opposite side, which is my y component, divided by the hypotenuse, which is 5. Moving things around again, I get Vy equals 5 times sine of that 60 degrees. Plugging this into our calculator gives us approximately 4.33 meters per second. So for how quickly they are moving eastward, that is our right, or x component. So that is this 2.5. And for our northwards, that was our upwards, or y component, which was this 4.33. Being able to take these kind of vector information problems and breaking them up into their components will be a key part of a lot of problem-solving methods in this class. Next, let's consider this example. A person travels 50 kilometers from city A to city B. Then 30 kilometers from city B to city C as shown. How far from their home in city A have they ended up? Also, what distance did they travel? This question ends up relating to how vectors add together. Visually, we add vectors from tip to tail. Each of the arrows here represents a displacement moving from city to city. I'll call the one going from A to B as our AB displacement vector. Meanwhile, the arrow moving from B to C, I will call our BC displacement vector. From the problem, we know the length of each of these vectors, AB being a length of 50 kilometers, and BC a length of 30 kilometers. If I add these two vectors up visually, I get what we might refer to as the resultant vector, which runs from where we originally started here at city A to where our final vector ends at city C. I'll label this as R for the resultant vector. This resultant vector is our displacement from A to C the magnitude of which will tell us how far the person has ended up from their home in city A. That means for our displacement, what we are looking for is the magnitude of that resultant vector, where that resultant vector is made up of the addition of our AB and BC displacement vectors. In order to find out anything about this resultant vector, we will have to add the vectors AB and BC by components, which means we need to break them up into their components first. AB is made up of some rightward component and some upward component, making our right triangle out of the AB vector. The horizontal or x component is the adjacent side, so this will end up giving us the hypotenuse of 50 times cosine of the angle 30 degrees. Meanwhile, for the vertical side, or the y component, ABY, this is the opposite side, which means the calculation we will do is 50 times sine of that 30-degree angle. So do make note that as I've broken up this displacement vector into its components, I've chosen a certain convention. The horizontal component is going to the right, so I'm going to leave that as a positive, so right is positive in the horizontal direction. And the vertical component, which is going up, I have also made the choice to call that as a positive direction upwards. So by making these choices, anything that is going leftwards in the horizontal direction should be a negative, or anything that is going downwards in the vertical direction should also be a negative component. Next, I need to break up the BC vector, which has an upwards vertical component, but a leftwards horizontal component. The horizontal x component is the adjacent side to our angle, so that means that BCx is equal to the hypotenuse times cosine of that angle. However, as we just mentioned, since it is a leftwards component, I need to make sure that this has a negative when I go to do calculations on it. Then for our vertical y component of the BC vector, that is the opposite side, so this will pick up 30 times sine of the angle 45 degrees. Since this y component is going upwards, and I have chosen positive as upwards, it should remain positive. Now that everything has been broken up into components, we are ready to get the resultant vector by components. So the horizontal or x component of the resultant vector will be the addition of the x components of the individual vectors. So the calculation I should be doing here is 50 cosine 30 minus 30 cosine 45. This will give us approximately 22.1, and since all of these displacement vectors have the same units they started out with, when I add them, we are still in kilometers. Next up, for the y component of our resultant vector, I want to add the y components of my individual vectors, meaning this calculation should be 50 sine of 30 degrees plus that positive 30 sine of 45 degrees. Doing this calculation gives us approximately 46.2 kilometers. So in other words, if we went directly from city A to city C, we have gone eastwards 22.1 kilometers and northwards 46.2 kilometers. But we're not done quite yet. We have the components of our resultant vector, but what we wanted is the magnitude of this vector. Since a vector is always made up of a right triangle with its components, Rx, Ry, with the magnitude being on the hypotenuse, we can use the Pythagorean theorem to get the magnitude. So the magnitude of our resultant vector will be equal to the square root of the Rx squared plus the Ry squared, which means plugging in at 22.1 kilometers squared plus the 46.2 kilometers squared. Add those and the square root. After doing this calculation, we end up getting that the magnitude of our r vector, which is the displacement, is 51.2 kilometers. The displacement answers the first part of the question, but now what about the distance traveled? Finding the distance is actually much easier in this case. the distance will end up just being equal to adding up the magnitudes of each individual displacement vector we took along our path. But these magnitudes were already given to us. From city A to city B, we went 50 kilometers. Then from city B to C, we went 30 kilometers. We don't care anything about the direction we're going or having to add anything as vectors. If we have gone each of these distances, then the total distance that we traveled is just the addition of both of them, which is 80 kilometers. For one last exercise, vectors are a good opportunity to reinforce the difference between displacement and distance. In this example here, we might be running around a rectangular track. Starting from the bottom left, we run 50 meters east, then 30 meters north, then 50 meters west, then finally 30 meters back south to end up back where we started. We could go and calculate the resultant vector made of these four individual vectors, the magnitude of which would be our displacement. The Rx component will pick up a 50 meter positive east direction. The Ry component then picks up a 30 meters north as a positive. But then our third vector goes back to the west. That is a leftward horizontal component, so that will contribute to our Rx, but it is leftward, so it will be a minus 50 meters. Then we travel south, which contributes to our Y vertical component. Downwards means it should be subtracted. So for both of our horizontal and vertical components, we end up seeing a 0 meter component. The displacement will then be the magnitude of this resultant r vector, which is the square root of 0 squared plus 0 squared, which will just be 0. Finding a displacement of 0 meters makes sense because displacement only cares about the difference between where we started and where we ended up. Since we ended up at the same place we started at here, displacement should be equal to 0 without even doing a calculation. Meanwhile, for distance, we did actually run all of these links. We ran 50 meters, then another 30, then another 50, then another 30. So we are getting this kind of workout around this track, so we should give ourselves credit for running a total distance of 160 meters. That will wrap up our video on vectors.